All right, so we're going to wrap up our derivatives, really all of our derivative rules today, by talking about some inverse functions. All right, so before we do that, let's do a quick little review. What do we know about inverses? First of all, with notation, for a function called f of x, its inverse is called, well, it's called the inverse of f, but it looks like that. Be very careful. This does not mean f of x to the negative first. I'm just going to write that kind of big there. Careful, because I see it all the time, right? That means the inverse. Who knows why the heck some mathematician somewhere said, let's use a -1 exponent to mean inverse. Drives me crazy. Okay. So what do we know about inverses? Well, a lot of things. Sorry. One thing for sure we know is, these are in no particular order, inverses are, and their relations, functions and their inverses are symmetric over the line y equals x. We'll see a few pictures of that today. If I asked you to find an inverse algebraically, you would switch the x and the y to find the inverse algebraically. And actually, that's how we find it graphically as well. You switch the x and the y coordinates. We could write it a little bit better than that. We could say point A comma B on f of x, we say it corresponds to the point B comma A on the inverse of f. Basically, it's just saying you switch the coordinates, and there it is. Okay. So let's start with a lovely little Algebra 1 type picture here. It says, pause if you need to, right? It says, consider these two inverse relations at corresponding points A and B. So I have this graph here. I'll do it in red. We've got this nice little line, and point A is the point 0, 2. And it says, find the slope. Well, the slope of that line, it looks like to go from here to here, I'm going up 1 over 2. Okay, well, let's take a look at its inverse. It's a thicker line. I'm trying to make it purple, but you probably can't tell. And here's point B. Point B is the point 2, 0. Oh, look at that, 0, 2, 2, 0. Corresponding points. The slope of the purple line, it looks like up 2 over 1. Okay. Just for fun, while we're here, let's throw in a little, I'm going to throw in an orange line here. Oh, maybe green, because it'll stand out a little bit better. I'm going to draw in that symmetry line, that line y equals x. Remember, one of the things I just said on the last slide is that functions and their inverses are symmetric across the line y equals x. You see that mirror image across that green line? That's just for fun. Okay. Great, so we did exactly what they said. They said find the slope at A, find the slope at B. All right, let's move on. Let's come back to that in a minute. We're going to do the same thing with two different graphs. So again, I'm going to make this first graph. This is y equals x squared, our lovely parent graph of a parabola. And here's point A, that's the point 2, 4. Now it's not a line, so if I want to find the slope, I need the derivative. So let's see, y prime equals 2x, which means the slope equals 2 times the x coordinate, which is 2. I'll circle that. So there's the slope at A. On the inverse, got this sleeping parabola, the equation is x equals y squared. Now, first of all, point B is the point 4, 2. Oh, look at that. 2, 4 becomes 4, 2. Let's talk about the slope. If I want to find the slope, I need the derivative. Look at that y in there. The derivative of x is 1. The derivative of y squared is 2y dy dx. Look at that implicit differentiation we can use there. So 1 divided by 2y is equal to the derivative. That means the slope equals 1 over 2 times the y-coordinate. My y-coordinate is 2, so I get a slope of 1/4. So when we go to the next slide, it's going to say, what did you notice about the slopes of the curves at corresponding points? All right, well, let's look at these. Here's corresponding points A and B. The slope was 4, the slope was 1/4. Excuse me. Come up here. The slope was 1/2, the slope was 2 over 1. Right? Well, look at that. They're reciprocals, aren't they? So what did we notice about the slopes of curves at corresponding points? They're reciprocals. Now notice, I did not say opposite reciprocals, just reciprocals. Okay. Now the question is this a coincidence, or will this always be true? Is this a special case? Will this always be true? Yes. Yes, it sure will be. And I have so many different ways I can show you, but here's the deal. If the slope is change in y over change in x, on the inverse, what did we say we do? We switch the x and the y. Wouldn't that become dx over dy? Reciprocals. So dy dx on the inverse will become dx over dy. We're just going to flip our fraction over, right? We're going to switch the x and the y. That's kind of nice, isn't it? So I'm going to write this a little more formally, and it's going to look kind of bizarre. But I'm going to write, this is going to look bizarre, I know, the inverse of f prime, so the slope on the inverse at A, will be equal to 1 over f prime of B. That's a little more formal. I think that's pretty overwhelming. I'm not saying I would memorize that. Let's maybe memorize it this way. Corresponding points, if I can spell, I wanted to put an I there for some reason. Corresponding points, there's my I, on inverse relations have reciprocal slopes. Maybe that's what we should memorize. Okay. This is a little bit overwhelming, but it's saying if you want the slope on the inverse at A, then you're actually going to need the y-coordinate on the original and find the slope there, make it a reciprocal. Whew! All right, so let's take a look at how they could ask a question like this. I say they, I'm talking about the College Board folks, right? Okay, woo! It says given f of -1 equals 3. Well, that's just a point, isn't it? And f prime of -1 equals 1/5. So here's a point on f. Here's the slope on f. In fact, at that point, isn't it? Well, let's just write this down. So on f of x, I have a point, -1,3, and the slope there is 1 over 5. Okay. Let's see what they're asking us to find. Find the inverse of f prime. So they want the slope on the inverse at x equals 3. So they give us the point on the original and the slope at that point. They want the slope on the inverse at a completely different point. Okay, let's come back to that. What we just learned is that if you know, by the way, this first part is pre-calculus, if on the original you have this point, that means on the inverse we have this point, right? We just switch the coordinates, corresponding points. And we also said at corresponding points, these graphs will have reciprocal slopes. So if the slope at this point is 1/5, the slope at its corresponding point will be 5/1. That's what we do know. All right, well, let's think about what they asked us to find. They said find the slope on the inverse. So on the inverse, find the slope at x equals 3. Perfect, we have that, right? This is x equals 3. We have the slope. So our answer is 5. I guess I could have written that a little bit better. The inverse prime of 3 is equal to 5. Same thing, the slope on the inverse at x equals 3. Okay? All right. So that's kind of a relationship between just any old graph and its inverse. What I would like to continue on with now is talking specifically about our inverse trig functions. All right, so it says, first of all, let's review the graph of inverse sine of x, and we should all remember that inverse sine can also be written as arc sine. They mean the exact same thing. So what I've done for you is I've graphed the original a sine curve. It looks like I'm going from like negative pi to pi, a little bit further out. And then I've graphed the inverse of sine. We spent a lot of time on this last year talking about, well, if you graph the whole thing, it's not a function. So we restricted the range so that it is a function. So this bold graph here is the entire graph of the inverse sine of x. Okay. They want me to state the domain of that red graph. Well, it looks like the domain is going from -1 to 1. Okay. So then it says, for what values of x does the derivative of inverse sine exist? If the inverse sine graph only exists between -1, then its derivative will only exist between -1 and 1. However, if this has a slope of 0 here and here, if I were to continue it on, these slopes would be vertical, which means we don't get to include there. The slope doesn't exist at the end point. Okay, we can certainly talk individually about that. I'm just kind of pointing that out. Okay, here's the deal. Let's say I want the slope on the inverse at 1/2 or 0.7 or -1/3. Our goal today for the rest of our notes is to find the rule. What is the derivative of inverse sine of x? Okay, well, the first thing is, let's start with the original, y equals the sine of x. That's the original function. The inverse would be found by switching the x and y, right? So if the original is y equals the sine of x, the inverse is x equals the sine of y. And I'm trying to find the derivative of said inverse. Well, let's take the derivative. The derivative of x is 1. The derivative of sine of y is cosine of y. The chain rule says multiply by the derivative of y, which is dy dx. Great, so let's divide both sides by cosine y to get dy dx by itself. Beautiful, so this right here, I'm not going to circle it, this is the derivative of inverse sine of x. It's okay. This is a function in terms of x, but then its derivative is in terms of y. Gosh, it'd be great if we could get it all in x, because then we could use the graph. Then, you know, we'd like things in terms of x better. So I'm going to come over here to the side. Remember how we said x is equal to the sine of y? Do you agree I could just write x over 1? Okay. Remember, SOHCAHTOA, sine means opposite over hypotenuse. By the way, I'm just showing you where this derivative comes from. You don't have to produce any of this proof again. So if sine equals x over 1, that means the opposite is x, the hypotenuse is 1. So I'm going to go draw a little right triangle, not to scale. And here I'm going to call this y, the sine of y. The opposite of x is x, the hypotenuse is 1. Okay, well, I would like to find the cosine of y. Right, here's angle y. If I want the cosine, I need the adjacent side. Well, let's use the Pythagorean theorem. I can say x squared plus, let's call that b squared, equals 1 squared. So b squared equals 1 minus x squared, or b equals the square root of 1 minus x squared. I know some of you are sitting there going, what the heck is she doing? I promise I'm going somewhere with this. Our derivative was in terms of y. I didn't like that. So I started saying, well, what's the relationship between x and y? And that used trig, so I drew a triangle. So I was able to find missing sides. So now I can say my derivative is 1 over the cosine of y. And look at my triangle. The cosine is the adjacent over the hypotenuse. Well, I don't really need to write divided by 1. So the cosine of y is the square root of 1 minus x squared. Woo! If our original function is the inverse sine of x, this is its derivative. Wild, isn't it? Now, we're not going to go through the other 5. I'm going to show you where they are. They're in your notes packet. If you flip to the front cover of your notes packet, right? Look at the back of that. Look at, oh, let me back it up here. Look at all these derivative rules. And some of you have seen those in there, right? So we've got our power rule, product rule, quotient rule, chain rule, all our trig derivatives. Up here, exponentials, logarithms, and here's our new ones. Oh, my camera froze. This is a big deal. We're going to walk through these together. This is the one we just found. We just said the derivative of inverse sine is 1 over the square root of 1 minus u squared. That means it doesn't have to be x. It could be anything in there. But then we have to incorporate the chain rule. Okay. Now, look at these two. What's the only difference here? The only difference is that there's a negative 1 on top instead of a positive 1. Oh, well, that makes that easy to memorize, doesn't it? Also it starts with the letter C, doesn't it? Let's clump these two together. This is the derivative of inverse tangent. It's 1 over 1 plus u squared. We'll do some practice with these. Inverse cotangent is exactly the same except for the negative on top. Oh, look at that. Also started with a C. We've seen that pattern before. And then these last two. They look miserable, don't they? We've got the derivative of inverse secant is 1 over the absolute value of u times the square root of u squared minus 1. And then the chain rule. The derivative of inverse cosecant is the exact same thing with a negative 1 on top. Wow, that's a lot to remember. Now here's the deal. They all have 1s and u squareds in them. 1 minus u squared, 1 plus u squared minus 1. Look at that. The order's going to matter, right? Here's the hint I have. See those u's side by side? That's what tells you to put the u first. Here, there's nothing out in front. In fact, the last thing you just wrote was a 1, so that's the first thing you'll write here. I don't know if that helps or not. Pair them up, okay? All right, let's take a look at some examples. So the first one says, I want the derivative of arc cosine, which means inverse cosine, of 4x cubed. Okay, here's what I'm going to do. I'm going to use a template, right? The derivative of inverse cosine is -1 over the square root of 1, see how those ones, minus blank squared. That's my u. So again, I leave the inside alone. So I put a 4x cubed in there. That just took care of the inverse cosine. The chain rule says multiply by the derivative of the inside, which is 12x squared. Lovely. Could I simplify that? I mean, I guess you could put the negative 12x squared on top, and on the bottom you could square that to get 1 minus 16x to the 6th. So if you really are looking to simplify, that's not too bad. Okay. Good. Let's take a look at the next one. Take the derivative of inverse secant of e to the x. So again, this is my u. That's what's on the inside. So I'm going to start with a template. Inverse secant is 1 over the absolute value of blank times the square root of blank squared minus 1. There's my template. The chain rule says we're going to leave the inside alone. Well, I had the inside twice in here, didn't I? So I'm going to put my e to the x in both places. Chain rule says multiply by the derivative of e to the x, which is, oh, that's e to the x. You can leave it alone. You can also simplify. Honestly, it simplifies really nicely. Now, technically, we can't cancel these because one of them's in absolute values. However, the absolute values are not necessary because this piece, this graph, is always positive. And if something's always positive, you certainly don't need absolute values. So I'm left with 1 over the square root of, let's multiply my exponents to get e to the 2x, minus 1. What we love, and I know you're probably disagreeing with me, but what we love about these is that the derivative of inverse trig has nothing to do with trig. There's no trig in there. And that's kind of nice. All right, let's take a look at the last one. So we see our arctangent or our inverse tangent. However, it's inside a square root. So the first thing we're going to need to do is write this as, I use inverse tangent when I rewrite it, the inverse tangent of x squared to the 1/2. Okay. Look at this big old set of parentheses or brackets, well, parentheses I should say, right? The outside was that square root. So we're going to deal with that first. I'm going to bring the 1/2 down in front. I'm going to subtract 1 from the exponent. The inverse tangent of x squared doesn't change. Great. Times. We just took care of the 1/2. Now, on the outside of the next set of parentheses is the inverse tangent. The derivative of inverse tangent is 1 over 1 plus blank squared. What was inside? X squared. Last layer of that chain. So we took care of the 1/2, we took care of the inverse tangent. We have not touched the x squared yet, and its derivative is 2x. You know what? Let's just put a big old box around that. Now, could I simplify this? A little bit, right? I have a 1/2 and I have a 2, so you can get rid of those. Other than that, maybe calling that x to the 4th, but it's not going to do much. That's why I just looked at that and said, all right, I'm going to be able to cancel the 2's. But after that, there's not much else I can do, so to me, I didn't feel like it was that worth our time.